Welcome to Hartman Math. Before we get to applications of trigonometry, let's go ahead and complete the warm-up here based on some of our trig graphs. Pause here until you're done. All right, so number one, we've got our cotangent function where the b has been factored out already. Period is going to be pi divided by b. So that's going to end up being 8 pi over 3. The phase shift, the nice thing about when the b is factored out is we're looking at the phase shift right here. Positive 8 pi over 9. And the average value, 2/11. All right, assuming that we're looking at a cosine function and also assuming that our a value is positive, what's the amplitude? Well, the center line or the midline is going to be right here, our average value line, and our maximum's 2 above that, so I'm going to say it's going to be 2. The period to complete one full cycle, maybe from there all the way back to there, so that distance is 3 pi. The phase shift, 3 pi over 2, assuming again that a is positive, so we can't be starting here, we have to be starting here as one option. So from there to there, as this is, each one is pi over 2, so we're starting at 3 pi over 2. And then the average value right there at 3. What about the equation for it? It might be easiest to write this in that factored form, where we say it's y equals 2 times, and then we got to figure out essentially the b. So if the period is 3 pi, and we know that's equal to 2 pi divided by b. Now we go ahead and solve for b. We're going to get 2/3. And again, probably easiest to write this in factored form, as here's our phase shift, there's our average value. This is lesson 4.8, applications and models in the trigonometry chapter. Example number 2, finding the side of a right triangle. I want to read through and then most importantly sketch and label. So pause here until you have that, the sketch and the label. It's going to end up looking like something like this. Maybe a few more labels to put in here, such as we've got our 72 degrees, we need an 84-foot ladder, it is 10 feet off the ground, unknown h here for our right triangle. So we're going to do some right triangle trigonometry, where the sine of 72 degrees is h, opposite divided by 84 hypotenuse. Let's go ahead and solve that for h. Multiply both sides by 84. Now we can use the calculator. Make sure you're in degree mode, as we're talking about 72 degrees. H is about 80. Now we got to answer the question, what is the max safe rescue height? Well, this is 80, about. But then we got this 10, 90 feet. Make sure we're labeling with units. 90 feet is our answer. Example number 3, finding the side of a right triangle. Once again, pause here as you read through, then sketch and label. A lot of people are confused by the smokestack thing, but that's what we see when we have talking about a factory with the tall cylinders where the smoke is coming out of. So we've got a situation that looks like this: 31 degrees here, 43 degrees here. And we've got a couple unknowns. We've got unknown height of the building, unknown height of the smokestack. So we'll need variables for both of those. We're probably going to need a couple different trig equations. We've got, for the 31 degrees, tangent of 31 degrees is x over 280. Tangent of 43 degrees is this side of the right triangle, so h plus the x So that we've got that equation and we've got that equation. So we've got two different equations. We are ultimately solving for h. So if we solve here, multiply both sides by 280 and then subtract the x, we get our height as a function of x. So we're going to need to know what x is. I think we can get the x from over here though. X would be 280 times the tangent of 31 degrees. So if we replace that here, the height would be 280 tangent 43 degrees minus 280 tangent 31 degrees. Now we can type it into the calculator, round to something that would be appropriate to the situation. We're definitely not going to say something like, I don't know, we're talking about in feet here, 73.21 feet. That would be far too fine a rounding. I think 93 feet would be appropriate. Example number 4. Fighter jet is flying at an elevation of and is 12 miles away from the aircraft carrier. What is the angle of depression? So the angle of depression, it's a really important vocabulary term, is from the horizontal, how much would we depress down as far as an angle to get to our desired site? So always, whether it's elevation or depression, always from horizontal. In this case, bending down. So as far as we're going to make our right triangle that goes from here to here, clearly we're going to draw a hypotenuse first. What about the other part? Well, we need a horizontal that's coming from the jet. So that's going to be the appropriate right triangle. We're looking for this angle right here. That's the angle of depression. We're going to label some sides. Now, the issue on our sides is they do need to be the same measurements. Here we got feet, here we got miles. So we're going to have to convert. It might be easiest to convert this one to miles. That is 1 mile. 1 mile, 12 miles. So now we're going to set this up. There's our theta. There's our angle of depression. So tangent of theta is 1 over 12. We want to solve for theta. To get rid of the tangent, we're going to do inverse tangent on both sides. And again, we probably want to be on degrees here. So make sure your calculator's in degree mode. Inverse tangent of 11 over 12. We're going to get an angle of depression of about 4.76 degrees. We want to be pretty exact on that because we don't want our fighter, it needs to be exact to land on a pretty specific spot there. We don't want them missing by 50 feet and landing in the ocean. All right, so another part of application, we're talking about directions and navigating. That's going to bring in bearings. And bearings can be measured in a lot of different ways, but our go-to conventional one, 95% of the time, is going to be, we're going to measure from a fixed north or south line. So our angle is always coming from north or from the south, and that's it. And then we're going to bend one direction towards either west or east. So what we would say as far as bearing here is we'd start with either the letter N or S, saying we're going north or we're going south. So either going up or going down. In this case, we're going up. So we'd say north, bend 73 degrees towards the east. So our bearing is going to be north 73 degrees east. What do you think about this one? I think it should be south 17 degrees towards the west. And one more. Careful. North, we need this angle, 58 degrees towards the west. All right, see if we can put that into use. So example number 5, finding direction in terms of bearings. A ship leaves port at noon and heads due west 50 knots. That means nautical miles per hour. At 1 p.m. the ship changes course to find the ship's bearing and distance from the port at 3 p.m. So we've got to kind of sketch this out, see what's going on. So we've got to start at the port. We're going to head due west for, well, if we're going from noon to 1, that's 1 hour. 20 knots per hour means we're going to travel 20 nautical miles. And then the rest of the sketch would be, all right, that puts us here. Then we're going to change bearing north. We're going to bend 26 degrees towards the west. So here's the north. Notice how I drew a north line. I also drew that here as well. Drew a north line, bend 26 degrees towards the west. How far do we travel? Well, from 1 p.m. to 3 p.m., that's 2 hours, times 20, 40 nautical miles. So this is what we have. And if that's 26 degrees, then this has to be 64 degrees. So we have these unknown lengths here in this right triangle, an x and a y that we can find out using this and this. So the cosine of 64 degrees would be x over 40. And the sine of 64 degrees would be y over 40. If we solve those, and notice I went pretty far because I'm going to do intermediate rounding here. I want to be as accurate as possible in my final answer. So I used a lot of decimal points here. All right, so now, by the Pythagorean theorem, now we can find the d, because now we know this length and this length. For the x, we're going to need to add 20 to it to get this full length here. So by the Pythagorean theorem, you can find out that's 52, approximately, nautical miles. And then the bearing, well, the bearing would be beta, touching the north line. But we're going to find alpha first. So alpha, well, we know y and this distance here, and we could say the tangent of alpha is y over that length that we just used in the Pythagorean theorem. So if we now do inverse tangent, alpha is going to be about 43.77 degrees. We want beta, which would be the complement. That's going to be our bearing angle. North, 46.23 degrees towards the west. And that's our bearing. Another application of trigonometry is in harmonic motion. Essentially, we have a spring with a weight at the end hanging down. And if we pull that down and then let go, it's going to oscillate here. And its position is given by trigonometric functions. Here's what we have. In this case, we have equilibrium, so it's just kind of no force is acting on it. It's just at rest. Maximum displacement in the negative direction, so pulling down. And as it releases, as it comes up, this would be its maximum displacement in terms of being positive. And then the functions for any of these harmonic motion problems, the displacement is equal to a times sine of, this is lowercase omega, times t, or same thing for cosine, where t is time. Typically it's going to be seconds. Okay, and that means that the period, this connects back to our other trig graphs, the period for both would be 2 pi divided by b, but in this case b is omega, so 2 pi divided by omega. Frequency is just the reciprocal of the period. And I'm talking about how many cycles that we get per second. So example number 6, simple harmonic motion that satisfies the condition. We're going to start here. Displacement, t equals 0. That's essentially going to tell us whether we're dealing with a sine function or a cosine function. So which of those is initially has a value of 0? That would be sine. Whereas cosine, the displacement will be either at its if it's t equals 0, it would be at its maximum or minimum. So we're going to deal with the sine function. Amplitude. right, that's probably telling us that A could definitely be 4. So we'll use that. And then the period is telling us, well, we're going to have to figure out, that's going to help us figure out omega. So according to the previous formula where period is 2 pi divided by omega, we'll set that up. 6 equals 2 pi divided by omega. All right, we want to solve for omega, so let's multiply both sides by omega. Divided by 6, we're going to be pi over 3. So that's going to go here. So we've got an answer. And that might not be the only possible answer because although the amplitude is 4, it doesn't necessarily say that A is 4. A could also have been what? It could have been negative 4. Instead of starting by going up, it could start by going down. So it could have been negative 4. That's also an acceptable answer. Example number 7, we're given the function. Let's see if we can determine some things about it. Like what is the maximum displacement? We're talking about amplitude. What's the frequency? Remember, the frequency is just the reciprocal of the period. So the period is going to be 2 pi divided by b. The frequency would be the reciprocal of that. So divided by 2 pi. So pi over 4 divided by 2 pi is pi over 8. Pi's cancel. So 1 over 8, and that means cycle per second. 1/8 of a cycle per second. So it would complete 1 cycle every 8 seconds. Find the value of d when t is 6. So let's go back to here. T is 6. 6 pi over 4 is 3 pi over 2. What's the sign of 3 pi over 2? Negative 1 times 5. Negative 5. And part D, find the least positive value of t for which the displacement would be 0. So my first thought is, well, we'll just replace d with 0 and see when is this going to be 0. Well, clearly, if we're talking about sine, 0 works, but that's not positive. So now we need to kind of know the next one. So where else will we get a value of 0? Well, we can get rid of the 5. We can divide both sides by 5. And then in terms of where is sine 0? Besides 0, in terms of thinking of our sine graph, where is the next place that sine is back on the average value line? We remember 0 and then hits again at pi. So I think we're going to have this be pi. Now solve for t. Multiply both sides by the reciprocal. We get t equals 4. That's our answer. That's it for today. See you next time.